Hello, is Liliana Corral, and in this work we investigated the effect of sodium modification on the reduction kinetics of nickel-manganese oxide oxygen carriers for chemical looping hydrogen storage. The main objective of this study was to determine how different sodium contents affect the structural characteristics and, particularly, the reduction behavior of nickel-manganese oxide at 700–800 degrees Celsius. Chemical looping hydrogen storage, or CLHS, is based on cyclic redox reactions involving a solid oxygen carrier. During reduction, the oxygen carrier reacts with hydrogen and forms a reduced solid. In a complete chemical looping hydrogen storage cycle, this reduced phase is subsequently oxidized with steam to produce hydrogen. Because of this, the reduction behavior of the oxygen carrier represents an important part of the overall process. Both the reduction rate and the achievable conversion determine the availability of the reduced phase for the following step. Nickel-manganese oxide is an interesting oxygen carrier candidate because of the redox interaction between nickel and manganese, which can facilitate lattice oxygen removal. However, its reduction kinetics can still represent a limitation. For this reason, sodium modification was evaluated as a strategy to improve its reduction behavior. Nickel-manganese oxide was synthesized by a coprecipitation method using nickel and manganese nitrate precursors, with a nickel-to-manganese molar ratio of 1:2. Precipitation was carried out at 60 degrees Celsius using sodium hydroxide. This was followed by aging for 12 hours, filtration and washing and drying of the precipitate. The resulting precursor was then calcined at 800 degrees Celsius for 6 hours to obtain the spinel phase. Sodium-modified materials were subsequently prepared using sodium nitrate, with nominal sodium contents of 1, 3, and 5%. Throughout this presentation, pristine nickel-manganese oxide is referred to as NMO. The sodium-modified formulations are referred to as NMO1 sodium, NMO3 sodium, and NMO5 sodium, according to their nominal sodium content. The materials were characterized using X-ray diffraction and scanning electron microscopy. Their reduction behavior was evaluated by thermogravimetric analysis. First, regarding the morphology, scanning electron microscopy shows strongly agglomerated particles in both the pristine and sodium-modified materials. After reduction, both samples show fine bright particles distributed over larger agglomerates, with a denser distribution of these features in the 1% sodium-modified material. X-ray diffraction confirms that nickel-manganese oxide is the predominant crystalline phase in all fresh materials. Rietveld refinement also indicates the presence of small amounts of sodium-containing secondary phases in the modified samples. A more noticeable difference appears after hydrogen reduction. Pristine NMO is mainly transformed into metallic nickel and cubic manganese oxide. In contrast, the sodium-modified materials additionally show the formation of tetragonal manganese oxide. Therefore, sodium modification is associated not only with changes in reduction kinetics but also with a different phase evolution during the reduction process. The reduction behavior was evaluated by thermogravimetric analysis under 10 volume% hydrogen and argon at 700–800 degrees Celsius. Sodium modification accelerated reduction at both temperatures. The inset graphs highlight the first minute of the experiment, where the initial rapid mass loss stage is more clearly observed. The mass changes were converted into fractional conversion to compare the materials quantitatively. All sodium-modified samples reached high conversion earlier than pristine NMO. The strongest overall improvement was observed for the 1% sodium sample. At 700 degrees Celsius, the time to reach 90% conversion decreased from about 15.8 to 3.8 minutes. At 800 degrees Celsius, it decreased from about 7.3 to 1.5 minutes. Importantly, increasing sodium content beyond 1% did not further improve the overall reduction performance. The conversion curve showed two distinguishable regions, an initial rapid stage followed by a slower stage. The rapid stage was described using a Boltzmann function. The parameter L represents the contribution of this stage, while tau represents its characteristic transition time. Sodium affected both parameters, with the 1% sodium sample showing a favorable combination of a large rapid stage contribution and a short transition time. The slower stage was analyzed using the Avraamierefeeve model, where K represents an apparent kinetic rate constant. Sodium increased this rate constant compared with pristine NMO, although the strongest effect depended on temperature. The 3% sodium sample showed the highest K at 700 degrees Celsius, while the 1% sample showed the highest value at 800 degrees Celsius. Overall, sodium influenced both reduction stages, but its kinetic effect was not proportional to sodium loading. A possible explanation for the kinetic enhancement is that sodium modifies the local lattice and defect chemistry of the oxide. Previous studies suggest that sodium can favor oxygen vacancy formation or reduce the energy required for lattice oxygen removal. Easier oxygen removal could therefore accelerate reduction under hydrogen. However, higher sodium contents can also promote sodium-containing secondary phases. These phase changes may partially offset the beneficial effect on oxygen mobility and defect chemistry. This could explain why the kinetic improvement was not proportional to sodium concentration and why the 1% sodium sample showed the most consistent overall performance. This mechanism remains a working hypothesis and would require further defect-sensitive characterization for direct confirmation. In conclusion, nickel-manganese oxide remained the predominant crystalline phase in the fresh materials, while sodium-containing secondary phases were detected in the modified formulations. Sodium modification significantly enhanced reduction performance at both 700 and 800 degrees Celsius. Among the studied compositions, the 1% sodium formulation showed the lowest times required to reach 90 and 95% conversion, and therefore the most consistent overall kinetic improvement. Kinetic analysis showed that sodium affects both stages of the reduction process. The Boltzmann analysis revealed changes in the extent and characteristic time of the initial rapid stage, while the Avraamierefeeve analysis showed an increase in the apparent rate of the slower stage. In addition, X-ray diffraction of the reduced samples revealed a sodium-dependent phase evolution. Pristine NMO formed metallic nickel and cubic manganese oxide, whereas the sodium-modified materials additionally exhibited tetragonal manganese oxide. Overall, the results indicate that a relatively low sodium loading can effectively promote the reduction of nickel-manganese oxide, potentially through changes in lattice oxygen and defect chemistry that facilitate oxygen removal. These findings provide useful information for tuning the reduction behavior of nickel-manganese spinel oxygen carriers for chemical looping applications. Thank you for your attention.